Morning everyone. So in this tutorial I want to introduce to you a very common chemistry technique. This is an analytical technique known as titration. The goal of doing a titration is to determine an unknown concentration. I'm just going to introduce to you some of the basics, and then what we're going to do is we're going to switch over to a virtual lab. I'm going to walk you through some of the terminology and actually show you how we can actually use the indicator, look out for what color changes that we're interested in, and towards the end walk you through a sample calculation. So to start off here, again, titration is our technique. Titration, the goal of it is, like I mentioned, to find an unknown concentration. Usually the titrations that we do are going to be acid-base titrations, but that could be generalized to a redox titration, it could be a chloride titration, solubility titration, but the goal is the same. I'm going to try to find the unknown concentration. The demo that I'm going to do for you is going to be an acid-base titration. The glassware that we're going to be pulling out later on here is going to be a long burette. A burette here has a stopcock valve here. You do want to make sure that it's perpendicular when you load up the solution. The burettes that we have are 50 mil burettes, exactly the same on the virtual simulation. The burette actually has numbers upside down, so the 0 mark is actually up here, the 50 mil mark is down here. Once you're sure that this stopcock valve here down here is closed, what I tell people normally is just fill out the burette here, something more than half. You want to just make sure you have enough solution inside here to accomplish the entire reaction without necessarily having to refill the burette. Every time you refill the burette here, you're going to introduce more error. Because of the markings as they are, we have the 0 mark up there, 50 mil mark down here. We're going to have maybe this mark here. We're going to make a starting reading. Let's say this reading here starts off at 10. I'm just going to zoom in what that part looks like there. I'm going to see the 10. I can see a tick, 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 5, tick, 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 tick. I can see it like that. I can see like 11. So the numbers are definitely going to be upside down. What we're going to do is we're going to be reading the bottom of the meniscus, especially if it's like a water-based solution. So as I look down here, I know I'm confident about I'm going to take this initial volume reading, VI. My initial reading is going to be at least 10. I'm going to go point, it looks like my bottom of the tick mark here is somewhere past the second tick mark, so 0.2, and then I'm just going to guess the other one here, let's say 0.25. Your burette readings can always be read to 2 decimal places. If you think about the error stuff that we introduced, however, we usually do half in the last digit. Because each of these ones here is off by a milliliter, I'm going to go plus or minus 0.05 milliliters. If you're more confident, you can make that tinier, but that would be a minimum error. Do that double check, make sure our error is 1 sig fig, perfect, and make sure that the error is lined up with our guess, so that's why it's a 2 decimal place number. So that's my starting reading, that's my initial volume. That doesn't mean, though, I actually have 10.25 milliliters in my burette. Like we mentioned, the numbers are upside down. I probably have about 30, 40 milliliters in here. But what I'm going to do here is I'm going to have my starting reading. After I'm completely done my titration, this solution here would have been dumped out a little bit here. I'm just going to make a new reading. And again, I'm going to have a final reading. I'm going to have a number read to 2 decimal places here. Maybe just for argument's sake here, 31.67. I'm going to associate that with an error. Again, even that number there doesn't mean that I actually have 31.67. That just means that that's what the label says. What I'm going to actually be doing later on is actually finding a difference in volume, the delta V. And basically by subtracting these two here, 31.67 minus 10.25, bigger number minus small number, it's actually the difference that I added. It really does mean that I've actually tossed in 21.42. If you remember your rules for errors, when you subtract numbers, so it's big number minus small number, your errors just inevitably get bigger. I want to say 0.10. We're going to round our error to 1 sig fig. Even though our burettes could have each been read to 2 decimal places, I'm stuck with then reading 21.4 plus or minus 0.1 with the units later on. And I'm going to tabulate this for you later on after I walk you through an experiment, but basically that's how you make your readings. It was a little bit hard to get this number. Afterwards, it's just going to end up as a stoichiometry problem. So in this demo here, what we're going to be doing is an acid-base titration. It's going to be very similar to, let's say I have HCl reacting with NaOH as an example of an acid-base titration. We would do a balanced equation. I produce a salt and I produce water. Sometimes the mole ratio is 1:1. You do have to do your own balancing here. But again, the whole goal here is I want to find the unknown concentration. In this case here, my first titration is actually going to be to standardize NaOH. So my unknown solution will be NaOH. Basically, you have a bottle of NaOH. For us in our virtual lab, it's going to be labeled, I know it's going to be approximately 1 molar, but I don't know exactly what it is. I want more precision than that. Is it 1.1 molar? Is it 1.12 molar? Right? I do want to know that precision. Or it could either be, well, I completely don't know the molarity. I have this bottle. Maybe it's really, really strong, right? I really need to be safe around it. Or maybe it's already been diluted with water. Titration, the technique, is to use to find this unknown concentration. What we're going to do here, we're going to see towards the end of our virtual lab, I'm going to be titrating. I'm going to put base in the burette. That's not a given, but I'm going to prefer to have the base in the burette, and therefore I can drop this base here into the acid. Although the acid, let's say for argument's sake here, the acid I don't know the concentration. Let's say it's question mark molar HCl. This thing here may be really concentrated. It may have a lot of H plus particles. Maybe it's already really dilute. I don't know. I'm doing this technique to find that out. But even though I don't know the concentration, it is totally up to me the volume that I use to actually put in. Usually we're going to be using a glassware called a pipette to actually do this delivering of the volume. Our pipettes are either in 10 ml increments or 25 ml increments. So even though I have no clue how concentrated or how strong the sample is, I can actually test. The volume totally up to me. I might want to test 10 milliliters or I might want to test 25 milliliters. How the titration here is set up, I'm just going to introduce you the basics and then show it to you on the virtual simulation. Basically, there is an unknown concentration I'm after. I have a bottle of HCl labeled. I don't really know what the molarity of HCl is currently, or even if I do know the molarity, I want to do it in such a way that I know it to more detail. This HCl is going to come with it a bunch of H plus in my 10 milliliter sample. What we're going to do is we're going to slowly drop in the base. I want to drop in the base in such a way that the base is going to help count the number of acid molecules that I have. So basically, as I drop in the base, I throw in the OH minus. I want the OH minus, if it encounters the H plus, that's going to undergo a neutralization, that's going to cancel out, and that's going to leave me, oh, I still have H plus around, drop more base. I want to look for the instant where when I drop more base, well, that base here can still find an H plus. If I drop another drop of OH minus, that OH minus here now can't find any extra H plus. I want to stop exactly at that point so I don't have an excess OH minus. At that point, we would have hit what's called an equivalence point. That's when I have exactly dropped in the same amount of base particles as acid particles. That's when it's completely neutral, there's no excess, there's no limiting. And in that case there, all our stoichiometry is worked out, and therefore we can just do a quick mole conversion and figure out how many moles of HCl and thereby figure out the concentration of HCl. Here's one other little problem is, unfortunately, both HCl and NaOH are both colorless solutions. Sure, ideally, right, I want to be dropping in the space, I wanted to kill off the H+, but seeing as everything is colorless, I wouldn't know when this, what's called equivalence point is reached. Maybe I can introduce that term for you here. We're looking for it to hit the equivalence point. Equivalence point is when the moles of acid, moles of H+, equals the moles of OH-. That's the perfect stopping point where you actually have no excess. What we're going to do is we're going to cheat a little bit. We're going to throw in a third ingredient, and that third ingredient here is going to be an indicator. Indicators we're going to learn in Chem 12. It's a weak organic acid or base, and basically for indicators, they have a different color depending on whether the solution is overly acidic or overly basic. For indicators, we introduce a very common term. We're going to call this the end point, or you can also call this the transition point. Obviously, you want to choose an indicator that has an endpoint transition point to change color close to the equivalence point that we're interested in. The endpoint is for the indicator. The indicator we're going to use is a chemical called phenolphthalein. So phenolphthalein. Right? Phenolphthalein here, every indicator will have different color change points here, but at least for phenolphthalein, you don't need a lot of it, so we're going to see us drop in a couple drops. It has one color. When it's an acid, it actually stays colorless, as is an acid. If I have slowly dropped in more and more base, it's going to actually switch over to its second color, which is actually a deep pink color. So this is kind of nice here. This indicator is actually going to switch. When it's still remaining acid, it's just going to stay colorless. It's as if it's not there. But when I have an excessive base, when I have dropped in more base molecules, if it senses those hydroxides around, it's going to suddenly change to a pink color. So what we're going to find is as we walk through this virtual simulation here, as I slowly drop in the base, at first the indicator is going to notice, oh, hey, there's a lot of hydroxide around. If that hydroxide, you swirl around the Erlenmeyer a little bit, if that hydroxide ends up finding H+, it cancels out where it would have temporarily been pink. Now it changes back to the acid color. As we slowly drop in more and more and more base, we're going to eventually hit this equivalence point where I actually have leftover hydroxide. It can no longer find any more H+. Because it can no longer find any more H+, the overall solution is basic, and that's when it's going to change to a pink color for good. I want to find the instant that this happens. I don't want to what's called overshoot my endpoint. I don't want to toss in a ton of hydroxide. Oh no, now I have an excess of NaOH. Now I don't have a good count of how much HCl there actually were there. That's the whole goal of a titration. I want to count how much HCl is actually present. If this HCl happened to be really, really concentrated, that would mean there's a ton of H+. All that would mean is I would need to toss in a bunch of OH- until the equivalence point was reached. If this was very dilute, I only need to drop in a couple of mils here, and it's already changed to this pink color. Depending on how much base I need to drop in until this color change happens, that's how I know when to stop, and that's how I know when to do our stoichiometry calculations. So just let me introduce to you here, this is actually the handout that they gave you for the lab here. I'm going to walk you through this on the virtual simulation. Hopefully this gives you a visual of what a titration technique is. In case you need review later on here, hopefully that'll serve as a good review as well. I borrowed this lab here out of UBC. So basically a bunch of universities got together and they designed a virtual lab software, a simulation. And basically what we can do is we can actually pull out glassware as we would in a regular lab here, use pipettes, use barrettes. They'll even animate the color changes for us here. A couple important notes here before I switch over to that simulation. Again, what we're doing is we're doing an example of an acid-base titration. There are others, but the whole goal is to find the unknown concentration. Now, even though they're going to roughly tell me what the concentrations are, they want to just sort of give me some hints going into it. I could have gone into this completely not knowing this number, but in this case here, the whole point of titration is to be really precise, even if they tell me. So the HCl that they give me is actually about 0.1, the NaOH that they give me is about 1 molar. I would still do a titration to figure out more decimal places, more significant figures, because one sig fig here really isn't a lot. What I want to do here is I want to get my standardized solutions to be close in concentration. If one solution is like 0.01 molar and the other is 1 molar, you're going to end up wasting a ton of solution before this color change happens. Or if this one here is overly strong for this one here that's not so strong, you're going to be doing it within a drop. Again, you're not going to get the right precision. So what they're doing is they're giving a rough number. When you actually create your standard solutions, we're actually going to get a sense of keeping the concentrations roughly close so that I'm not necessarily wasting over one solution over the other solution. So let me just draft out for you how this is going to look like, and I'm going to demonstrate it for you on the virtual lab. We're going to start off with a primary standard. So there's some language here that you might want to note down here. A primary standard, I think of it, this is a solid. And what's so special about a primary standard? A primary standard is something that is very, very pure. It's very, very unreactive. So if you leave it exposed to the atmosphere, it doesn't react with water, absorb carbon dioxide, or anything like that. So the good thing about a primary standard is because it has all these nice quantities, if I measure a certain amount of this primary standard, this time we're going to use a guy called potassium hydrogen phthalate. I'm going to show you the calculation in a second here. If I measure, let's say for argument's sake here, if I have 1 gram, I'm going to use KHP as a shorthand for that. If it's 1 gram, and I know chemically speaking this is very, very pure, I'm pretty confident that the entire 1 gram is actually the chemical that I'm interested in. If this thing here were impure, let's contrast that with something that's not a primary standard. Let's contrast that with NaOH instead. NaOH here is notorious for absorbing water from the atmosphere here. You might be able to still put it on a scale. You might be able to still record down 1 gram worth of mass. However, because it's been absorbing water away from the atmosphere here, we're actually not going to get the right precision. We might go through the calculations thinking it was 1 gram, but unfortunately NaOH here is very impure. NaOH here would not be good for a standard. So back with our primary standard here, I'm going to take my KHP. I'm going to show you how we're going to make a solution of it. Because this mass here is very well defined, I know 1 gram is actually this compound. However much volume that I make it up to, I'll demonstrate for you the right procedure of it. This now is going to be called a standard solution. That word here, standard, just means it's something that I know the concentration very well. Turns out for a titration, even though the whole goal of a titration is to find some unknown concentration, you have to know one of them. There can't be 2 unknowns. This primary standard here happens to be acidic standard. What we're going to do is we're going to take NaOH, just solution that they give me. They told me earlier the NaOH here should have been roughly 1 molar NaOH. I'm going to create a standard KHP solution. So my acid solution, I'm going to have roughly 1 molar KHP. I can even change that number a little bit. Not exactly 1 molar, but I'm going to have roughly 1 molar KHP here. I'm going to know the KHP concentration really, really well. And then in doing the titration technique, I can figure out how many base particles that I need to count the acid particles to hit equivalence point. That way I can standardize. Here's the verb of it. I'm going to use KHP, that's step 1, to standardize the NaOH solution. I already knew the NaOH was sort of like 1 molar. When I say standardize, I mean find the molarity even better, right? So 1 point however many. So use KHP to standardize. NaOH as solid was the impure standard. I wouldn't start there, but once I make a solution, I can do this titration technique to find the precision on NaOH better. And then what I'm going to do in step 2 is, now that I know the NaOH is standardized, I can actually take that very same NaOH. I might need to refill the burette in case I'm running out. But if I now know the concentration of NaOH to a lot of precision, let's say for argument's sake here, 1.234 molar, really, really high precision, I can use that, what's now called a standard solution, right? The NaOH here has now become a standard because I know the concentration. I can use that to titrate my last sample here, which happens to be an unknown HCl. Again, they give me a ballpark. It's roughly 1 molar, 0.1 molar. I might need to actually dilute it down, but now that I've standardized it, I can use that in a titration to figure out the unknown concentration. So the whole point of titration is to use something I know the concentration to figure out something that I don't know the concentration. Because NaOH had this problem of it wasn't a nice primary standard, it wasn't a good solid to work with, we actually needed to start off with this KHP. So let me just demonstrate this for you on the virtual simulation. We'll switch over to that. So this here is our virtual lab environment here. I'll do in another video how we can download the software here and how you can access these solutions. Assuming that you've done that here, on our OneNote so far, we've been looking at the sort of problem description on our handout. You can actually access that description here. Pretty much we're trying to do an acid-base titration. We're using KHP as our primary standard. That's a really pure solid that if I make a solution of that, I'm going to know the concentration really well. We're going to be doing 2 titrations using this KHP here to figure out the unknown concentration of NaOH. They help you out a little bit and they say the NaOH is going to be roughly 1 molar's worth. But the whole point of doing a titration is to figure out, well, what more significant figure is 1.1, 1.12. I want to know more digits there. Once I have standardized the NaOH, I'm going to use that solution to standardize HCl. So if I go back to my workbench here, my lab environment, just like in a wet lab here, you can pull out a whole host of different glassware. So I'm going to first make my standard solution here. Maybe I'll need a beaker. I'll even pull out a volumetric flask. Pull out a 100 ml volumetric flask here. Beakers are really good sort of carrying tools here. You can start measuring masses in beakers, but unfortunately the markings on the beaker here are not very precise. So I do want to demonstrate to you the proper technique of making a solution here. Volumetrics here, even though they do only have the one single mark, these ones here have been really well calibrated. By the time you add water to that mark, bottom of the meniscus hits 100. I know it's exactly 100.00, 2 decimal places volumetric class. So I'm going to pull up my solutions here on the left sidebar here. I have my KHP, my acid, as well as my NaOH. My first titration is going to be between KHP and NaOH. So let me just pull those 2 out first. KHP, it comes to me as a solid. This is a bottle. That's why I'm going to need to make a standard solution first. This one here was my primary standard. It was the pure solid. If I make a solution, I know the concentration really well. NaOH, in contrast, also starts off as a solid. But unfortunately, because it's absorbing water from the atmosphere, when you weigh out, let's say 1 gram of NaOH, I'm not confident how much of that 1 gram is actually NaOH. So what I'm going to do is I'm going to do 1 set of titrations just to start off with the chemical that I know, KHP. Let's standardize the NaOH. Let's find that concentration really well. And once I know that NaOH really well, I can do another titration, use the NaOH now that I've standardized. Now I know the concentration really well. Use that to actually standardize, find the unknown concentration of HCl. So sort of 2 titrations in one. The calculations end up as a stoichiometry problem later on. It's just a little bit more work to actually get to those numbers. So let me first demonstrate to you how we're going to make our primary, start with a primary standard KHP and make our first standard solution and start into our first titration between KHP and NaOH. So what I'm going to need, because KHP here is a solid, I'm going to need to pull out a mass balance. So I'm going to pull out a scale here. Our scales here will only read up to 1 decimal place or 2 decimal places. If you go on to chemistry, there is what's called an analytical balance, which can actually measure 4 decimal places. So this is not crazy. Do make sure that the scale is tiered or 0 to begin with. I'm going to start off in dissolving my solid. It's good to do the dissolving process in a beaker. The beaker here has a very wide mouth, so if you take a stir stick here, it's really easy to dissolve in there. Obviously, the beaker itself has mass. I don't really care for that mass there. In fact, even if beakers are sized the same, if I have 5 250 ml beakers, every beaker itself has its own mass, so you will have to put that individual beaker, tear that scale before you actually measure the KHP. For me to transfer KHP, I'm going to start with the KHP. I'm going to drag it over the beaker. On the bottom here, I have a nice transfer bar. I can actually type in the number, the mass that I want to transfer. I calculated if I want to make 100 mils of my standard solution, I want to toss in 18.38 grams. You can either press enter or you can press pour. As I pour that in there, the scale there should read, oh, perfect, 18.38. You might be a little bit off. Maybe I calculated 18.38 and we got 18.40. Just change your number to 18.40 when you do your calculations. That was an approximate anyways. Now, I know I'm going to make the standard solution here into a 100 ml flask. I don't necessarily want to just take out my jug of water and just add 100 mils here. Like I said, if it just says 100 mils on the beaker's marking here is not very precise. The more precise one is actually volumetric. What I want to do here, why I measure it into beaker first, is I actually want to do the dissolving part. So what I'm going to do, I know in the end it's going to be a total 100 mils. I'm going to add the water, so drag the water over top the beaker. I'm going to pour in something less than 100. So I'm just going to make the dissolving happen. Maybe I'm going to transfer in, 30 mils at a time. So 30 mils of water, I'm going to pour that in. It's going to take a little while for that solid to actually dissolve. I don't necessarily actually need it on the balance anymore. I don't need the actual mass of the balance anymore. But basically, I've dissolved in 30, something way less than 100. I'm assuming you're going to take a stir stick and actually mix this up, start mashing up the powder a little bit here. KHP is an alkali salt, so it should be fully soluble. And what I'm going to do is I'm going to transfer that 30 ml of solution. I'm going to pour that into the volumetric. It already zooms in for me. This one mark here would be 100.00. Well, I only had 30 in there, so let's just transfer in 30 mils. So there you go. Basically, all of it's there. You'll notice, hey, I still have some solid or some liquid left over. Well, that was only 30 mils, and I'm not up to the mark yet. Sometimes the dissolving isn't quite complete. I still have some solids left over. Here you can even add some more water. Just make sure the total water that you add is something totally less than 100, and that way I can add it up to the mark eventually in the volumetric flask. So I've added another 30 or so. Maybe use your stir stick and dissolve it a little bit more, break up some of that powder. Again, when you're ready to transfer it in here, I'm going to transfer in another 30. Looks like I have, maybe a little bit more. I'm going to see if I can transfer extra. Pour all of those rinsings here into the volumetric. Just make sure it's less than the 100 mark, because I'm going to make it up to the mark in the more accurate, more quantitative volumetric flask. So assuming you've done that rinsing process a couple times, I've fully dissolved it. I now have my powder pretty much dissolved. The reason why I don't dissolve it fully in the volumetric is this long, narrow neck here makes it really hard for you to put your stirring stick inside. Fortunately for us, we've done the pre-mixing in here. And now what we're going to do is we have our volumetric. Now we're ready. Usually you use a dropper for this. Okay, I'm just going to pour in from the water here into the volumetric flask. At first, right, I added in 30, and maybe I'll add in another 10 or so. I just want to make sure that I'm under the mark. As I'm getting close to the mark here, maybe I only want to add maybe 1 ml at a time. So I'm going to add in, again, you probably wouldn't do this with a big jug of water, but as you see me pressing enter and pressing pour, this one here is steadily climbing upwards. I'm getting pretty close to the mark. And as I get right up close to the mark, it's actually best to actually take out an eyedropper, take out one of those dropper pipettes here, and actually drop it in really, really finely until bottom of the meniscus is exactly 100. I might overshoot it here. Let's just take a look here. So I'm going to add in, maybe with a dropper pipette, I'm going to add in maybe 0.5 mils if I can. I'm going to try to get it as close as I can so that when it hits bottom of the meniscus, hits that 100, I know this is exactly the concentration that I wanted. If you happen to overdo it, now, even though the KHP was a very pure solid, I wouldn't be able to really measure accurately. Well, what extra volume did you add? You can't take out that water again. You would actually need to redo this dilution procedure. So definitely really, really precise towards the end so that you want to make sure the bottom of the meniscus actually lines up with 100. Now I have my standardized KHP solution. This one here, I made it. This is going to be roughly 0.9 molar. I was told that the NaOH was about 1 molar. I made these very similar so that I'm not going to be wasting a ton of one chemical or a ton of the other chemical. At this point here, I'm ready to do my titration. So for my titration, what I'll need is I need to pull out my burette. For my burette, burettes also come in many sizes. Most commonly, it's going to be 50 ml burettes. For us, the reaction is going to be between KHP as well as NaOH. I'm going to just choose to put the base in the burette. You could totally put the KHP in the burette as well. It would work exactly the same fashion. In this case, you remember the 0 mark is on top, the 50 ml mark is on bottom. I'm just going to fill it up something more than half. So I'm going to drag the Erlenmeyer with the unknown NaOH, drag it over the Brett. If you need a funnel, you can pour that in that way. I'm going to pour in, let's say, 40 mils. Again, when I have a good 40 mils in the Brett, the marking on the Brett actually doesn't say 40. With the 0 mark up here, I'm only up to the 11 mark here. I read this to 2 decimal places. Let me actually just track down this number here. Volume initial, I'm going to read 11.2, maybe 24. I'm going to have that plus or minus 0.05. That's my starting reading. That 11.24 again doesn't mean I actually have 11.24 in the Brett. It's just my starting reading. After my titration is done, I'm going to read it again. By subtracting and finding that difference, I'll actually realize how much solution I've actually made. So that's my Brett, based in the Brett. For my Erlenmeyer on the bottom, I'm going to pull out a 250 ml Erlenmeyer flask. My volumetric flask here, this is now my fully standardized solution. I now have that volume really accurately 100 milliliters. At this point, you're welcome to put it back in the beaker. As I pour into a beaker, don't be surprised that, let's say I pour the 100 mils exactly back in the beaker. Don't be surprised if it doesn't actually line up with exactly the 100 ml mark. We said beakers, they just give you a rough approximation of what the volume is. I'm not exactly sure it's going to be 100.00. I already made sure the 100.00 in the more accurate volumetric. I'm just pouring it back to a beaker because it's a little bit easier to transfer with a pipette. So I'm going to pull out a pipette here. A pipette is almost acts like a straw. Pipette will come out to us in many different sizes as well. I'm going to decide to use a 10 ml pipette. Most of our pipettes are 10 mils. Basically, this acts as a straw. I'm going to put this pipette in the solution. Even though I've calculated the concentration of KHP here, I'm not going to be testing against the entire solution. I don't need all the base to kill all the acid. I'm just going to kill 10 mils of this acid. And just using stoichiometry, I'm going to figure out what's the relative proportion between the KHP and the NaOH. So I'm going to drag my pipette here into the beaker. Again, there's that transfer bar on the bottom. Because this is a 10 ml pipette, I'm going to transfer in 10.00 if I can. This time, instead of just pour, like kind of dropping out solution, I can actually withdraw. So I can suck up the solution. The pipette, like the volumetric, is really, really well calibrated for. So you notice this 10 is actually 10.00. I know this concentration very well. I'm going to transfer that 10 into my Erlenmeyer flask. So doing that there, right? I have my Erlenmeyer. Usually for a titration, I want to do it, repeat it multiple times. So while I'm at it, I'm just going to pull out 2 more Erlenmeyer flasks. Yes, with the magic of a virtual lab, you can even Control-C, Control-V. I just want to demonstrate to you how you would do this in a regular lab. So let's take this pipette here. Let's pipette out again 10 mils, withdraw solution. Let's transfer into the 10. So that's my second container. And then let's do that one more time. Let's take that pipette. Usually we like 3, so that way I can compare, was it a fluke that I got a certain number? In this case here, I'm just going to drag my pipette. Now I have 3 solutions ready. 10 KHP solution that I know really well. You should label these ones here so you don't actually get mixed up. And basically we're ready to do our titration. KHP is our acidic standard. It's going to acid base neutralize with NaOH. We mentioned I need to cheat a little bit by adding phenolphthalein. Phenolphthalein is an indicator. You won't need a lot of it. This one here, it can come to you as solid, but pretty much it's going to be in dropper form and solution form anyways. I'm going to drop in this just into my Erlenmeyer flask. Because in the Erlenmeyer flask, it's an acidic solution, it's going to stay colorless. As I slowly drop in the base, however, it's going to actually animate when that color change actually occurs. So let's just take this phenolphthalein here. Let's go to my 3 containers. Let's add in, let's transfer maybe 3 mils. So a couple drops. Doesn't matter exactly. I just need it present in each of the containers. A very common problem in titration is people forget the indicator. They start tossing in their base and they're like, hey, how come it's not changing to pink? Well, if you don't have the indicator, it's not going to change to pink. So there you go. Looks like I'm set it up. So I have my 3 indicator solutions inside, and now I'm ready to do my titration. For my titration, I have my about 1 molar NaOH. I'm going to drag my Brett here over my first trial. I had already recorded this down as 11.24. The first trial is usually just an approximate. It's usually just to get a sense, how sure am I this is 1 molar? Did I really calculate this concentration? Is it really going to be 0.9? What I would do here is I would be a little bit more generous with sort of opening the stopcock here, let a lot of solution come through, get a sense of how quickly the color is appearing or disappearing. In this solution here, maybe I'll transfer it 1 mil at a time. On my second trial here, I'm going to do a little bit more precisely as I get closer to the final volume. Let's say I transfer it 1 mil at a time. I basically open and close the stopcock valve. So I transfer it in here. You're going to see this number here on the side here continue to drop. I dropped in 1 milliliter, At first, it may have turned to pink, but there definitely was enough acid. The acid kills off all the base particle. Overall acid, the indicator is still staying colorless. So I keep transferring the solution in. Watch this volume itself drop. So the burette volume is dropping. Again, the first one is a little bit sloppy. And okay, so now I've hit a pink color. I probably overshot at this point. I would still take down this reading so I know approximately what it is. So my V final currently, I'm going to read, it's going to be 21 point, just going to change the number a little bit, 26 plus or minus 0.05. So if you do a quick difference between the 11.24 and the 21.26, I've added in roughly about 10 milliliters. This one here would be overshot. This one here, I've added in way too much base. Now there's extra base that can't find acid. I don't have excess base, and I don't have a good count of how much acid molecule there is. You would just dispose of that solution here. If you know you still have enough solution in the burette, we can now just drag this burette here over for the second trial. This time I'm going to do it a little bit more precisely. I'm going to take my initial volume. I'll copy all these numbers down for you later on as well. 21.26 plus or minus 0.05. I know it was at least 10 milliliters. I'm pretty safe with, let's say, dropping in 8 milliliters. So maybe either in increments of 8, I can still do it. So I can go, I recorded my initial volume, I can pour it in 1, 2, 3, 4, 5, 6, 7, 8. Or you can even just type in the 8. I know somewhere between 8 and 10 I overshot. Maybe instead of dropping in 1 mil at a time, 1 mil is actually one of these steps on the scale here. You'll notice your burette here is a lot more fine-tuned than that. Maybe I want to drop it in at a rate of maybe just 0.5 or 0.1. It actually gives you that precision to do that. So let's try 0.5 here as I pour it in, right? So it still hasn't hit here. Now I'm about 9 mil. I'm worried about overshooting. So what I'm going to do here is I'm going to start dropping in even less volume. Maybe I'm going to drop in 0.1 if I can. I'm going to look for when the pink color first appears. You'll notice this drop here is not happening all that quickly anymore. As I just drop this in here, 0.1, 0.1, 0.1, I'm looking for the first instant. If you did this in real life, the pink color would be staying for longer because the base is having a hard time running into acid. But I'm going to keep pouring it in until that faintest pink color shows up. And this pale pink color is exactly what we want. I'm going to take a reading again. And this burette volume reading, when did that occur? You'll notice my second volume, again, I'll jot these numbers down for you later on as well. 31.00. I'm just reading off the side of the burette what it's saying. So 31.00, 31.0, I'm going to guess maybe 0.03 or so. Again, I'm going to associate error of 0.05. So you see that one here, first thing, it hasn't overshot. We haven't gotten fully pink excess hydroxide. We actually saw the first instance of color change. That color should last on the order of about 15, 20 seconds or so. And that way you know to stop. And that way you'll know to be able to do your stoichiometry. Because I did have a third trial set up, let me just do one quick calculation. How much volume did I toss in there? 31.03 minus 21.26. I tossed in 9.77. So for my next trial, again, I know I'm safe with at least 8. So I'm going to have my third container out. I still have enough solution in my burette. If I at one point didn't have enough, I would refill it first. I'd take a new starting reading. Maybe I'll demonstrate that for you here. In my burette so far, it's 31. I actually know I have enough, but just in case you were worried I didn't have enough, what you can do is you can pour in more NaOH. It's just you don't want to refill kind of mid-titration. It's at the 30 ml mark. Maybe I'll refill it with about 20 or so. Now I'm back up to the 11 mark. You can even fill it up some more. Oops. Okay. So we have, now it's overshot. Let me actually try that again. So totally, if you're not in a titration, you can reload all you want. And you can pull out a fresh burette. That's fine. This time I'm going to pull in NaOH. Let's pour in, 35, right? So something totally different. You just want to make sure you have enough inside this burette for one titration so you're not reloading mid-titration. So in this case here, I was worried I didn't have enough, so I take a new starting reading. I now look like I am at 22.82, give or take, plus or minus 0.05. Now for my third trial, I'm going to take this one here. Again, I was confident. First trial, 10 was overshot. 9.77 seemed to be good. I can even transfer in 8 really quickly. You can save time. Pour in 8, right? Did that go in? No, not yet. So pour in 8, and therefore, it hasn't overshot yet. But as I get closer and closer to that color change point, I want it to be more and more precise. Again, with the magic of a virtual lab here, we can actually add it in like in smaller increments, like 0.5. I'm going to add 0.5 and 0.5. Maybe that's 9 mils. I'm going to maybe add it in 0.1 like we did last time. I can do this maybe 0.1, 0.2, 0.3, 0.4, 0.5. And maybe I want to go even more precise than this. Maybe I only want to drop in 0.05. It's like a partial droplet here. I want to get as fine-tuned as I can. When does this pink color finally first appear? So as I just dropped that in here, We're starting to see a hint of pink here. If you're not sure, add an extra drop here. There we go. We've hit this pink color. We definitely haven't overshot. This is a good reading. So I'm going to take down this reading, and I'm getting here 32.62 plus or minus 0.05. All right. So with that, we're going to switch over to the OneNote. I'm going to crunch through these numbers for you. We'll see how we do, make sure we understand the technique of a titration, and then we'll come back to this just for practice here. How can we actually do the dilution, and how can we do the second set of titration? Okay, so here we are back on our OneNote here. I'm just going to show you some of the calculations that we did, and then as well use some of that titration data. At first, I do want to show you what is this KHP standing for. KHP here is known as our acidic primary standard. KHP is actually a chemical here, potassium hydrogen phthalate. So a very fancy name here. The formula is KHC8H4O4. And what we care is the molar mass is actually 204.22. So when I actually first made that solution, I actually used that molar mass in my calculation. The one other thing we need to watch out for here is if I did the balancing equation, it's a little bit hard for you to predict in this case. This one here is actually a monoprotic acid. Basically what's going to happen in our balance equation, our KHC8H4O4, that's our KHP, we're first titrating it with what I believe to be 0.1 molar NaOH. We're doing this experiment to figure out what that concentration actually is. This one here will end up becoming just the sodium salt of this one. So NaK C8H4O4, and we're going to produce water. No surprise there because it's an acid-base neutralization. So let me just, again, walk you through some of the numbers I've been calculating so far, and then I'm going to show this to you as a stoichiometry setup. If you remember at the really beginning, let's do this in a couple parts here. First part here was making my standard solution. So this is the dissolving of KHP. What I did is, if you just backtrack my numbers here, I dissolved in 18.3 grams. Sure, I needed to do those couple rinsings in the beakers and all that, but eventually I dissolved 18.3 grams in my more accurate volumetric flask. The volumetric flask here, it's really well calibrated to be 100.00 milliliters. So let's figure out what concentration this starting amount was. So question mark concentration of KHP. I'm using the square bracket for concentration. I'm starting off here with 18 grams. So if I have 18.38 grams, I'm going to need the molar mass. So we said earlier, if you add up all those bits, 204.22 grams for a given mole. And then what we're going to do, this part here will feel a little bit weird in terms of our unit cancellations. We're very used to top unit cancels bottom unit, top unit cancels bottom unit. In this case here, my final unit is actually supposed to have a moles on top, and we actually just need to pick up a liters on the bottom. Eventually, this mass here all got transferred into the volumetric. The volumetric was 100 milliliters. I'm actually just going to divide it by 0.100. That's 100 milliliters in liters. What goes on top then? It's actually just a 1. If that confuses you, you can actually just do this first part. Just do the 18, divide the 204, and just do divide 0.1, and that'll give you moles comes out of here, and we're doing moles divided by liters. So doing that, I have 18.38 divided 204.22 divided by 0.1. I get a concentration. Keep your sig figs, right? The whole point of this is being precise. The analytical balance actually gave me more precision. I'm just going to treat it as a 4 sig fig number. There's 5 sig figs there, so 0.90000 molar. I calculated it roughly because they told me my NaOH here was roughly about 1 molar solution. I wanted the KHPs to be pretty close. I could have made it 1 molar, but why not? Let's just do 0.9 molar. Now what we have here is I have a standard solution. I know this concentration really well. I know it's exactly 0.9000. If you keep going in the decimals, there's some digits as well. But at least already to 5 sig figs, I know the concentration really well. Then let's think about doing the titration. The titration involved, just reminding you again, the titration involved starting with 10 milliliters of my KHP solution. So I knew the concentration, I knew it was 0.9, and I'm actually going to toss in 10.00 milliliters of it. I've decided to test enough KHP to fill 10 milliliters. So there's H+. There is an NaOH that I'm going to slowly drop into the solution. I know it is roughly 1 molar. But the goal in this question here is actually to figure out what is that exact molar, what is that to a better precision. So you saw me do this in 3 different trials. here's how the titration data is typically set up for you here. I'm going to actually show you trial number 1, 2, and 3. This one here is the initial volume. We're going to tabulate the final volume. These are the numbers that the burette themselves say. And then what we're going to do, most importantly, is actually find a difference in volume. And this difference in volume is actually the milliliters of NaOH added. So in some sense, the numbers themselves, they actually aren't given the full story. I had the 0 mark up above, I had the 50 mil mark down below. I just take one reading, take another reading. By subtracting the two, I actually figured out how much did I actually transfer. So I copied those numbers down on the side here. 11.24 plus or minus 0.05. First one here is sort of a, let me just get an approximate how close to my volume the titration would need. So 21.26 minus 11.24. I'm getting the difference is 10.02. If you remember, this is the one that became overly pink. Sure, because of the error, I need to write this as 10.0. And I'm going to write down some qualitative observations. When I did that first just approximate trial, I had overshot this one. This one here had become overly pink. So it's totally okay for you to drop this. That just gave me a ballpark. 10 is too much. Then what you saw is when I did test 2 and test 3, I did somewhere close to 10. I did maybe 8 mils safely. And then as I got close to this 10 mark, I started dropping them in smaller increments. Maybe not 1 mil increments, maybe half a mil increment, or maybe 0.1 mil increment. And when I recorded that down, because I didn't reload between these two here, my initial solution would say 21.26, so that's convenient. And then as I did the second trial, as I was a little bit more precise, close to the end point, close to the color change point, this one was only 31.03. I do that difference again, 31.03 minus that, I'm getting 9.77. Again, the error here, even though individually the errors were 0.05, because the errors end up adding when I do a subtraction, I'm stuck with then saying, actually I'll leave that there, I'm stuck with then saying 9.8 plus or minus 0.1. I knew my first reading here was overshot, so totally okay to ignore this one here as an outlier, especially if you are not the experimenter and you're finding, hey, one of the numbers is very different from the other two, totally okay for you to drop that before you take the average. At this point here, we were mentioning I actually do have enough. It's only going to take another 10. I have some 20 mils still left in the burette. But what I did is I tried to refill it. At first, I refilled too much. I can even pull out a new fresh burette here. That's totally okay. As long as you're not mid-titration, you can refill the burette all you want. When I refilled it, that's why my starting number is a little bit different. 22.82, that's what my burette said. As I got really, really precise close to the endpoint, this last number here was 32.62 plus or minus 0.05. So those are the numbers that we got from our titration. This one here gives me 9.80 plus or minus 0.1. And again, I'd round that 9.8 plus or minus 0.1. So definitely some really good consistency here. These two numbers, no guarantee they had to be the same. It was realistically 9.77 and 9.80. But if I were to just find one average, just for reproducibility in science here, maybe one was too high and one was too low, I would just average these two. So I'm going to make that note here. You just average close trials just to maintain that precision if you can. This is, in the end, how much base you actually use for your titration. And at this point here, the rest of it just becomes a titration stoichiometry problem. So if you think about it here, KHP is going to react with NaOH in a 1-to-1 ratio. In case the balance equation here is not 1-to-1, you do need the mole ratio. I'm just going to write this here as NaKP, and then I have water. Basically, it's the H and the OH there that actually neutralize to form water. And now this is just a basic stoichiometry problem. If I took an average between the close trials, I'm going to totally ignore the 10. Well, the average is going to be 9.8. The volume that I use for this is 9.8 plus or minus 0.1. The burette gives me things in milliliters, so that's going to be a volume. The concentration, remember we had standardized the solution for the solid. It was a really well-known 0.90000. Okay, so 0.90000. We're using that to find our unknown concentration. I'm going to leave that as question mark molar. But I just found that the volume, oh sorry, I did this wrong. This one here is the volume of actually NaOH. So sorry, this volume, this 9.8 plus or minus 0.1. Sorry, that refers to NaOH, so it's always good to just double check where you put your numbers. That was the base that I was dropping, that's why that number should go there. How much acid did I use? Remember, we had decided to use 10.00 for my pipette. Sorry, this one here should have been 10.00 to begin with. So, at this point here, it's a basic stoichiometry problem. I just hit the endpoint. the stoichiometry ratios are just perfect, that this has killed this, there's no limiting, there's no excess, and now we're ready to find what is the molarity of NaOH. I am fully expecting it to be somewhere close to 1 molar, but now we're going to have it to a little bit more precision. So let's try this out. I'm going to start off with the chemical that I know more things. So let's start off with the KHP. 10 milliliters, I'm going to write that in liters, 0.01000 liters. This is KHP. I'm going to use the concentration. The concentration is going to be, for every 1 liter, there is 0.90000, very, very precise. I do need to do the mole ratio. In this case here, for every 1 part KHP, it gives me 1 mole of NaOH, so it's a mole to mole ratio. Again, this part here feels a little bit weird because we're actually going to be just picking up a 1 over. Well, what's the volume that you actually divided in? I divided in 0.0098, which is the volume 9 mils in liters. I'm just going to ignore the plus or minus for the time being, just so that we get a sense of how do we get the concentration. Type in all the numbers, 0.01 times it by 0.9 divided by 0.0098, and that gives me here, oh, the concentration of NaOH was actually 0.91837. That's really, really accurate, but again, we're limited by a little bit of precision. Still, unfortunately, because our errors are actually so big, usually what we try to do is we try to get the titration volume to be at least 10 milliliters, so that way I have at least 3 sig figs. In this case here, because I really only have 2 sig figs here, I'm still stuck with it. Not only is this not even 1 molar, I'm stuck with it saying, oh, 0.92. Sure, it's a little more detail. It would have been nice if I can keep like 0.918 molar if I could. So what I want to show you here is that's how we sort of work our way through a titration. I showed you on the virtual simulation how we actually collect the numbers. I'm going to follow this up with another tutorial just to finish off the other titration. You can just do that for a quick practice, just to rehash your technique and then see if you can practice the stoichiometry yourself. Thanks, guys.